right, when it gets nicer outside. But welcome back to another installment of PyData Ann Arbor. I want to say that looking at the registrants or members of our group, we have now just surpassed 700 people, which is fantastic, in less than a year, right? And hopefully continuing to grow more. I'd like to obviously thank everybody involved in sponsoring the event. So obviously NumFocus for sponsoring the PyData group itself, TD Ameritrade for offering up this fantastic space, as well as Midas for the food that you're consuming. So whenever you see them, always tell them that we're having such great attendance as well as talks. For people that are new here, remember that there are a couple of emergency exits. There's one right behind this whiteboard over here, as well as just outside the door to the right. Okay, so in case of emergency, take the stairs. We're always continually soliciting for feedback as well as for speakers. So if you know somebody who knows somebody, please reach out and help us make those contacts. And everything that we do here is tracked on our GitHub page. So hopefully Katie will share some of those valuable slides afterwards, and you can find it there or on the associated website. And just like before, unless your questions are quick, please try to keep them until the end. And also remember that you're in a borrowed space, so take care of it. Get rid of any garbage that you have left over. There are garbage cans near the where the food is. I'd like to read our PyData Code of Conduct, so especially for people who are new. PyData is dedicated to providing a harassment-free meeting experience for everyone, regardless of gender, sexual orientation, gender identity and expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of meeting participants in any form. All communication should be appropriate for a professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate for any of our meetup events. Be kind to others, do not insult or put down other attendees, behave professionally. Remember that harassment and sexist, racist, or exclusionary jokes are not appropriate for PyData. Attendees violating these rules may be asked to leave the meetup at the sole discretion of the meetup organizers. Overall, thank you for helping making this a welcoming and friendly environment for everybody. So with that, I'd like to do our icebreaker. So for this month, our icebreaker is, because there's a bit of a Midwest contingency today, I'd like you to turn to either the person to your left or to your right, introduce yourselves, and tell them whether you prefer pop or soda, or neither, neither, either, either. Okay? So go ahead, introduce yourself. This month in data science. So I'd like to highlight SciPy. It is coming up in Austin, Texas, July 9th to 15th. And I believe today is the last day to submit your abstract to give a talk or a presentation. But otherwise, go and sign up and attend. I will be attending for the first time. I know Katie's a veteran at this, and you might want to ask her what her thoughts are. And also, TD Ameritrade is hiring, so please reach out to Logan Alstron up here. His team is hiring has a couple of open recs for a data science position. So, and next month we have another great speaker, Holden Corral. Will be talking about big data with Apache Spark, and that's on March 13th. Please sign up. We're about half full right now, but I'm sure that's going to fill up quickly. And then without further ado, I have a sort of a co-host today. So I'd like to introduce Dr. Patricia Schuster. You want to come up? Dr. Schuster is from the University of Michigan and is the reason why we have our guest today, and I'll let you introduce our speaker.
Today we're very happy to welcome Professor Katy Huff, who's now at the University of Illinois. So I knew Katie when we were at UC Berkeley together. I was a grad student and she was a postdoc. So she is very well known in nuclear engineering for her work in fuel cycles, but she's also well known in scientific computing and data science for her work in open source and reproducible code development. So we're happy to have her here this week. She's speaking tonight at PyData, and tomorrow she'll be in the nuclear engineering department at 4 p.m. in Cooley Building if you're interested to hear about her work in fuel cycles. So please help me welcome her.
Thank you. Thank you. Thank you so much for being here. Thank you, Sean and Patricia, for having me, and Ameritrade in general, and NumFocus, and Midas, and, you know, we have some really amazing people like Charlie here, who's also been part of my little visit. So thanks, everyone, for being so welcoming and lovely. So I'm going to talk today about my perspective on best practices from the context of like a scientific computing perspective. I hope that's interesting to you guys. How many of you have a science degree? Yep, exactly, right? You're all in your little hearts, true scientists. How many of you would describe what you're doing right now as science? Yeah, some very large percentage. So that's awesome, and it's exactly what I expected in a university town full of brilliant people. So I'm pretty excited. Hopefully this is helpful to you. I know a lot of you are really well informed about scientific computing, even reproducibility, open source, Python, etc. But I would just say that some of the things that I've come across have actually been sort of interesting. Among the dust, there are some gems. So I'll be talking about doing our best as scientists. All right. So Patricia mentioned this. So I've been a lot of places. I was at the University of Chicago and the University of Wisconsin. I was at California, Berkeley, and now I'm in Illinois. I'm really involved in the American Nuclear Society. I've written some pieces of code like Moltres and Cyclist and Perk and Pine, and I run a research group that's related to advanced reactors and fuel cycles, and I'm affiliated with the National Center for Supercomputing Applications, and I used to work for the Berkeley Institute for Data Science, but I'm not going to talk about any of those things, I think. I'm primarily going to talk about my experience in mostly the open source scientific computing universe, right? And my experience with that has been with SciPy. So Sean just mentioned, and I'm super glad that he did, the Scientific Python Conference in Austin, which is my favorite place. It's like going home, not just because I'm from Texas, but also because it's full of really amazing scientific computing folks who've written all of the packages that you rely on almost all the time. They've written NumPy, and they're hanging out there. They wrote IPython and Jupyter. I know you guys had a few great Jupyter talks over the course of this year. So you're really on board with that, and I think if you're interested in those kinds of things, you're going to find the authors of all those packages at SciPy. And in fact, one of the best parts of SciPy is not the conference, but the sprints afterwards. So you can stick around for a few days at SciPy, continue to enjoy the great state of Texas, and contribute to open source projects during the sprints. So there's 2 days of sprints at the end of the conference where those developers of NumPy and others like SciPy packages, Matplotlib, Pandas, like you've got Jupyter folks, you've got a whole fleet of people doing all kinds of really cool stuff. Numba, Dask, all those guys are at SciPy and they want your help. So guys and girls, guys and people. Okay. There's another organization that I'm super involved in that's called the Hacker Within. It was like an organization that I helped to found when I was a graduate student, and it's dedicated to graduate students finding the hacker within themselves. They may be learning to be a physicist or a biologist, but they're going to have to be a hacker to get that PhD. So they got together and sort of like there's a lot of peer learning, and so a lot of the lessons that I'll talk about in this talk come from that really fun group. Also, software carpentry and data carpentry, now called the Carpentries. I haven't updated my slide to their new logo, which is like a cool wrench thing. How many of you have heard of software carpentry or data carpentry? Yeah, of course, right? It's like, so software carpentry and data carpentry are great. They are for educating scientists about how to use computers properly. It is an extremely important organization. I thankfully was helpful like in the initial stages of that organization, and it really changed me as a scientist. So I really hope you guys get involved. I'll also talk a little bit about some of the lessons that I've learned from being an editor at JOSS, which is the Journal for Open Source Software. We're pretty new, but I'll talk about sort of what that means. But it's basically a journal where people review your software. Think about it. It's pretty great. I'll talk about some of the lessons learned from writing a book with my friend Anthony Scopatz, who's an amazing person, and a book called The Practice of Reproducible Research, which I wrote with some of my colleagues at this Berkeley Institute for Data Science that I mentioned. So this is the stuff that I'll be talking about, not all that other stuff about my real career. This is my fun part. All right. But I will briefly just tell you what nuclear engineering is. So I will just say, like, since many of you are going to say to yourselves, well, I wish we were talking about a little bit of science, I will say the science that I do is on fission, which is when a neutron strikes an atomic nucleus, and that atomic nucleus gets very excited. It's got an extra neutron, and it splits apart in its thrill, and it's got a little extra heat that it kicks out, as well as a few neutrons, usually 2 or 3. And we use those neutrons to then hit more atomic nuclei to get what's called a chain reaction, all right? And it's not just a Keanu Reeves movie. It is driving nuclear reactors, which heat up some water, that then heat up other totally clean, untouched water. That water typically spins a turbine. That turbine spins a magnet inside a coil of wire, which is also known as like a power generator, and it powers. In this case, it appears to be Seattle. Okay, so that's nuclear engineering. You now understand more of nuclear engineering than most of the public. I don't know why this is so tiny. This is supposed to be this beautiful big picture. So this is a great, beautiful wind simulation that's done like entirely on an open source stack, and I'm just going to use it as the background for the following slides so that you can enjoy it. I'm not responsible for it. This is from the nullschool.net, but it's a wind simulator, and I'll share this link to my slides at the end so you can go and play with it because it's super cool. It's got a lot of layers. This is the pretty layer. Oh, see, now it's like zoomed. Okay, something about HDMI is freaking out. All right. So what am I talking about? So science can do a whole lot, much more than we can imagine, right? We put a car into space a few weeks ago, right? It's pretty wild. But as recently as 1895, really well-educated people thought that even just flying machines at all were impossible. 1895! That is not that long ago. You know, there are like 115-year-olds still, you know, and they just, you know, they were thoughts in their parents' minds in 1895. It's not that long ago. So we can really make some amazing innovation in science, but scientists really rely on criticism and organized skepticism. So I'm going to talk a little bit about how you can build that into your software as a scientist. Ultimately, this is all for a purpose. Science, we care about, typically because science drives things in our world. It puts cars into space, right? But it also changes our public health scenario, changes our power scenario, it makes our air either clean or not clean. All of these things are very, very important. And so we need really evidence-based conclusions for these kinds of things. And so science itself is the sort of bulwark of all of this. And it's supposed to build and organize knowledge and test explanations about the universe. It's supposed to do so systematically and objectively and transparently and reproducibly. And otherwise, you really just can't call it science, right? And science, ultimately, it relies on peer review, right? You have to be able to look at each other's work and say, is this true? And skepticism, the inherent belief that even though they are your friends, your colleagues might be making mistakes. Transparency, you need to be able to share all of that information so other people build on it. Attribution, accountability, collaboration, impact. Since the 6th century BCE, the entire domain of science has been perfecting these tenets. And it is my opinion that open source software is now superior at all of them. Okay? So let's talk about it. How, why, what's science going to do about it? I apologize for anyone who saw my PyCon talk because there are some borrowed slides here and there. But bear with me, there are new slides in this talk that weren't in that talk. So don't worry. In my opinion, computers should help with efficiency, reducing human error, automating the mundane, simplifying the complex, and accelerating research. But scientists aren't very good at them. This is why open source is getting better at it, is that there are these tools that can help us accelerate what we're doing. But scientists are trained to be scientists. Most scientists have not taken programming classes, particularly scientists my age or older. I never took a programming class. My entire day is programming, writing about programming, reviewing code, teaching programming, and discussing some of the simulation results. It's all about the software. So, what are we going to do? There's this great quote by Victoria Stodden. who's a fabulous professor at the University of Illinois, and she says this very succinctly, and so I would just say that this is it's a great thing to sort of think about, is that computational science is a special case of scientific research where it should be easy to replicate the results. It should be nothing but sharing the files. So, interested in this sort of general feeling about the need for reproducibility in science, the tools that we have at our disposal, and generally speaking, the total ineptness of scientists because we were not trained. A lot of amazing people and myself wrote this great paper called Best Practices for Scientific Computing. So I'll go through some of the lessons. We give 10-ish lessons. The first one is write programs for people, not computers. All of these lessons are supposed to help scientists make their code more producible. Why would writing programs for people, not computers, help? Any ideas? It's going to be really interactive. Readability of this code. A program should not require its readers to hold more than a handful of facts in memory at once, because people don't read and interpret large things well. We read about a paragraph at a time. Think about, why are paragraphs even in text? Why do we have paragraphs? Yeah, it's because we can't hold more than that in our minds at a single moment. We should try to make names consistent, distinctive, and meaningful, and generally have good coding style. So for this means use style guides and make meaningful names. And, you shouldn't have functions that are exceptionally long. Your functions should be like a paragraph in length. You should let the computer do their work. So Greg Wilson, who of course is the first author of this paper and a fabulous human and founder of software carpentry and all of these things, his favorite analogy is that you're great at going out to the movies. You're great at thinking creatively and walking through the park. And the computer is not great at these things. But it's great at chugging the same calculation over and over again with minor parametric changes. It's great at sorting your files for you. It's great at globbing various strings together. But your time is better spent out at the movies with your sweetie, okay? So make the computer do repetitive tasks, save recent commands in a file for reuse. Use a build tool to automate workflows. It is raging hot in here, and I would just say that everyone's going to need to stay alert. So to help you guys stay alert, I'm going to introduce various little interactive activities. One of them is, what is your favorite build tool? You have 10 seconds. Turn to your friend. Tell them. All right, okay, don't waste your energy. Don't waste it. All right, this sounds like great. I heard make, I heard bundler, I heard various scripts. Anyone else? Snake make. Very good. Anything else? This guy said waft. Waft? All right, waft. I'll look into it. So yeah, build tools like help to automate your workflows. The classic is make. You might configure your make files with like autoconf and automake, or like if you don't hate yourself, you might not. Who knows? Make incremental changes. So one of the things that so this paper in general relies on a whole bunch of like meta analyses of various software experiences. So like they studied software engineers, they studied scientific computing folks, and one of the things that was found to be the most influential on keeping bugs out of the code was making tiny changes rather than very large changes. So that one's pretty easy. Small commits. That's your undo button. That's the size of your undo button. Obviously, use a version control system. Anyone here not using a version control system like Git or Mercurial or SVN or CVS or even really, really, really ancient ones? If you're not using one, like let's just chat afterward. It's gonna be great. Like there's nothing to be afraid of. Git has the most hideous, like non-intuitive commands. We're gonna get through it together. It's true. It's gonna be fine. But yeah, talk to me after if you're not, because it's gonna change your life. All right. Okay, don't repeat yourself. But I'll just say that, all jokes aside, scientists don't use version control systems. They're afraid. It's too hard. Most scientific PIs are not willing. They have 17 folders of final, draft reviewed by so-and-so. It's just not going to work. So don't repeat yourself. Everyone knows this, this is like a refrain in programming, is the dry principle. Modularize code. Reuse your code instead of rewriting it. Every piece of data needs a single authoritative representation in the system. These rules feel really obvious to people who've seen them before, and they are not obvious at all to people who haven't. And so, as scientists, you sort of have to step back and share with your colleagues these kinds of rules that say, it is easier to introduce a bug if you are copying and pasting it all over your code. And then when you fix it once, where are you going to have to fix it? All over your code. So unfortunately, you're going to miss it once or twice. So if you have it in just one place, then a bug can only exist in one place. It won't exist all over the universe. And so this is a key piece of knowledge, okay? Plan for mistakes. Scientific code typically doesn't defend against user error. User error is just a thing that, when you run it, you deal with it at that moment. I would say that, good scientific code does. It adds assertions for programs to check their operation. It does unit testing. You don't have to invent your own unit testing framework, and in fact, it's a bad idea. Use an off-the-shelf unit testing framework for whatever programming language you use. Y'all are getting sleepy again? Turn to your friends, 10 seconds. What's your favorite unit testing framework? And if you don't know what a unit testing framework is, explain it to your, or vice versa, have your buddy explain it to you. Go! Yeah, PyTest. That's a great question. I might want to address it. Kind of. It's hard to know what the answer is. But if you have small enough functions, yes. But should you do test-driven integration testing? No. You don't know what the ultimate answer is. So no. But for unit testing, absolutely. Yeah. I'll mention it. Almost always, if you make the function smaller, I've found that it's okay. I may be a simpleton, though. It could be the case that only works for me. Okay. All right, don't waste your energy. You guys are producing 60 watts apiece. Don't get too excited. So I had a great question, actually. One of the best questions ever, actually, just came up. So should you use test-driven development for your scientific software? Test-driven development is where you write the test that says, hey, this is exactly what I expect this function to do for various interpretations of its parameters. It should throw an error. If I give it strings, it should average them. If I give it a list of numbers, it should throw a non-implemented type. If I throw it a list of complex numbers, something like that. Should you do it for science? In science, you don't usually know the answer before you start programming. But for small enough functions, you should. So if your code is written with small functions, then you should know the answer for how each of those small functions behave. You may not know how the clock works, but you should know how all the gears work. Does that make sense? Sweet. So you may not have good test-driven development on the integration test side, but you should have it on the unit test side. Did anyone have any favorite test frameworks? Mine's PyTest. It used to be nose test, but it's no longer supported. Anyone else? JUnit, yeah? All right, cool. So we'll talk about R in a minute, but there's some problems there. Premature optimization is a problem for scientists. It's very hard to approach a problem and not to try to do it as well as possible immediately. Everything we've been trained to do, and you would probably agree, is to always win and always get the right answer better than everyone else in the class every time. It's actually better to try to just do the stupid simple thing, do a little agile work, and then fix it up and make it better later. Because writing code in the highest level language possible, like Python, is going to save you time. Not trying to perfect it the first time is going to save you time. And actually using a profiler to identify any kind of memory bottlenecks is going to work better after you've written the code, not before. Because you can't run the profiler if you do it before. Huh? SnakeViz, that's right. So profilers, lots of great profilers for Python. SnakeViz is great for visualizing it. KernProf exists. If you're not working in Python, you might use Valgrind, and you'll get used to the output eventually. Cool. You should document things for design and code purpose, but not mechanics. What do I mean by that? So one of the things we found was the documentation is really unhelpful. We didn't find this actually. This is like kind of a meta paper where we read a whole bunch of papers to determine what the right answers were. And a number of researchers have discovered that documentation that describes how a templated class is implemented, these are not very helpful for the user of those templates. It's much more helpful to say like what that thing is supposed to do and how you use it and like what the concept is. So interfaces and reasons, not how it was implemented. Documentation isn't the place for describing implementation. First of all, if you change the implementation, now you also have to change the documentation. Boo. You should refactor code in preference to explaining how it works. So when you change code, you should make sure it becomes more clear as you do so. And you should try to embed the documentation for a piece of software in that software. So, of course, you should be using doc strings in Python. You should be using like well-formatted doxygen in your C++, et cetera, et cetera. All right. That helps you make an automated documentation website. All right. Collaborate. Review code before you merge it. Use pair programming when bringing someone new up to speed and tackling particularly risky problems. Use an issue tracking tool. This feels really reasonable for people who are currently working in the software industry. It might be hard for scientists. So this is really important, I think, for today's software industry. And they would never think of not reviewing code before merging to master, probably. I hope you guys don't do that. There's like websites out there relying on you not doing that. But in science, it's actually really hard to get people to volunteer their time to review each other's work. And this is where we really start to see open source succeed, where academic science is failing at peer review. It should be the case that if your scientific code is out there in the world and your colleagues and at other institutions are interested in what you're up to, there should be some incentive for them to look at what you're doing and check that it's right, just like they would a peer-reviewed article. They spend some time, they look closely at it, but it's really hard to incentivize that with software. There are a number of things in the way, different software stacks, different capabilities. Ultimately, there's no prize at the end. Even if you're at a national lab and you're all sort of working together on a team, it's different than in academia, like where there's sort of a little cutthroat. It's still very hard to incentivize things like pair programming and peer review for code. And so this is one of the places where you have to tell scientists that this is the right thing to do for less buggy software. And this will create less buggy software. But it's very hard. It's very hard to convince. Yeah.
Do you make somebody a co-author if they simply did a code review?
That's a great question. Do you make somebody a co-author if they simply did a code review? And I'd say that's going to vary by research group. In my research group, they end up in the acknowledgements unless they contributed to the software, like in a direct fashion. But that may change over time if there are significant... So right now, the only people who do reviews typically are the people involved in those pieces of software. So like my research group is pretty tight per software project. But I think it's a really good idea to think about how people are acknowledged. And that would be a great incentive for people to do code reviews, because then they could conceivably end up as a co-author, particularly if they have substantive review comments, right? If you do have substantive review comments, you're effectively an author, right? Yeah.
So in a classic open source environment, the review is basically submitting a pull request.
Yeah.
And that's extremely well documented. Say you are using GitHub.
Yep.
If I use your software, I find a bug or I need a new feature, I write it, do a pull request. If you accept it,
yes,
I'm now an author, whether you accept it or not.
True. So, if you're using your fork, and you've committed to that fork, like, you're an author. He was saying, like, because of the way pull requests work, whether or not I ever accept the pull request for certain licenses, if you make commits to your fork, I never even have to pull the pull request for you to be an author of that code. And in fact, you are, in a sense. You are an author of that secondary code. And I actually do recommend very permissive licenses like that for academia. So I use BSD3 for all of my software, which allows people to do exactly that. And all they have to do is attribute me when they attribute themselves to their new version of the code. But yeah, incentives are tricky in academia. Very tricky indeed. Sorry, I want to watch the time so that I don't waste you guys' lives. Okay, so I'm going to move on from that best practices in scientific computing paper, and I'm just going to sort of talk a little bit about some of the things that I like to tell scientists that sort of came out of this book that I co-wrote with my friend Anthony Scopatz, who is more famous for his work on a text editor called XO and a shell called Conch than he is for his really great work in nuclear engineering, just because he's so good at this other stuff. Not because he's bad at nuclear engineering, because he's just a really amazing all-around human. I'd say that all this skepticism and stuff really falls into what you need to do to get started. So I like to tell people there's sort of a good, better, best. Good, pencil and paper, better, spreadsheet. But you have to tell scientists it's best to use a standardized data format, like a database or management system. In lots of scientific domains, there are very specific data formats that people use. If you're in Astro, you might use FITS files. In nuclear, you use these evaluated nuclear data sets, etc. But you should manage them in a real DB. Okay, so you guys know that. You should back up files with version control, not with hope or emails to yourself. So one of the things I like to tell my scientific colleagues is actually there's this, some people are very successful at managing all of their files by just emailing themselves every night before they go home, those files, so that if their computer ever dies, it's not a problem. But obviously version control. Managing changes. There's naming conventions, there's clever naming conventions, and then there's local version control. Clever naming conventions can get you pretty far, actually. So keep that in mind. But obviously, this is how version control works. I'm going to skip a couple of these because I think you guys know some of them. Instead of doing analysis with spreadsheets or some sort of commercial off-the-shelf package, you should probably use open source libraries because they can be debugged. Because even Mathematica and MATLAB have bugs, right? If you don't believe that, think hard about who you think works at MATLAB. All right. Check out Pine. This is a great example for nuclear engineers or scientists for what it looks like to sort of build a whole open source stack in science. Right. You should do scripted batch editing. So I don't know what everyone's favorite scripting language is for cleaning data, but cleaning data is a huge part of science as well as data science. I don't mean to put that in quotes, but this whole large field that you guys are changing the world with. So I don't know what you use, but I use a lot of sed, knock, and grep, but that's because I'm old. So I like Bash and Python as well, but actually my first programming language was Perl, so I write only code sometimes. Yeah. So for executing workflows, you could retype a series of commands over and over again. You could put them all in a bash script and run that every time, or you could use a makefile system, which checks whether or not you even really need to run that command before it then tries to run it. Right? So that's the whole purpose of things like make, is to avoid unnecessary typing as well as unnecessary CPU usage. So make is going to keep you from using CPU hours that you don't need on tasks that have already been completed for which all the dependencies have remained the same since the last time you did it. So make, autoconf, automake, cmake, etc. So I'm a very big fan of cmake. That dig at autoconf and automake was because one day, after years of autoconf and automake, I discovered cmake, and I was like, wow, you can write configuration files in English. That's great. So data structures. This is one of the key things that I think I struggle with actually as a professor. My students are really amazing people, but they want to put everything in a list. Everything. They want to put keyed dictionaries in complicated sets of lists that are named with different variable names, which should be the key in a dictionary. And it's obvious to me to look at it and I say, okay, clearly this should be a dictionary with all of those variable names. Those should be the keys in that Python dictionary. And it just isn't really very intuitive for someone who hasn't seen the flexibility of a lot of these data structures. And so using the right data structure for the thing that you're doing, that is half the battle. Because iterating over a keyed dictionary, it's going to be a lot easier than iterating over 45 variably named lists. I like to tell nuclear engineers this because it's distressing to know that in Fortran, they may also be using like vectors rather than arrays. In C++, there's maps, vectors, decks, etc. Obviously, I think in Python, the power is in dictionaries and NumPy arrays, but it's going to depend on your language. Let's skip over a few of these things. Sorry, I'm supposed to be able to skip some of these, but I'll just say API design, small testable functions. We talked about this a little bit. A lot of people write a lot of single blocks of procedural code. It's not great. Code proliferation is bug proliferation. I like to tell people variable naming is one of the most important things. So obviously the biggest perk of being a programmer is you get to name something every few minutes. But you should do it properly, right? Good, fine, but better, right? You should create a class that holds points if you're going to hold a point type object. Don't create 3 variables called x, y, and z and expect that everyone agrees that it's like Cartesian coordinates, etc. File I/O, a lot of general science software is going to have a lot of hard-coded variables that only work on someone's machine. If they're stepped up, they're going to have one plain text input file, and that's going to be sort of parsed line by line by their own homemade string parser. Obviously, the better is some sort of pile parsing library or argparse, something like that. You're going to have some input database instead. For example, you could use real languages that are intended for this kind of metadata, like XML, which has relaxed grammar structures available, or JSON or whatever. So I'd say just don't do the hard-coded variables thing. I'm going to skip a couple of these things. I'll just say in each of these chapters, sections, there's various pieces. Different scientists are going to use different pieces better than others. Obviously, for error detection, you want to have a unit test suite. And instead of just rereading the code to diagnose errors, you should use a linter and a debugger and a profiler. So we've sort of covered some of these things, but I'll say that if you want to look over these, I don't want to keep you guys since this is raging hot. But I'll just say there are a lot of tools listed in this talk for some of these things, so give it a look. So for collaborating, obviously I think that GitHub is the answer. I say obviously. Maybe some of you are into Bitbucket. What's up?
Where does a configuration language like YAML fit into this?
Yeah, so YAML totally fits in a lot of places. So you can use that instead of XML in a lot of places, but you're going to use it at the top of a lot of files for various other purposes. So I've actually seen a lot of very clever use of YAML. So on the back end of this website, for example, this presentation is a website that's rendered with reveal.js, and you can actually use Markdown to serve up some of these slides, and those Markdown files can have YAML headers to help. So it's in there all over the place if you're doing things right, but I would say that anywhere you would previously see something like an XML, you might think about a YAML or a JSON or something like that. Yeah, it's a great question. Right, peer review for code, etc. I want to move on to JOS though because it's more fun. Oh, I should move on to this briefly. Okay, sorry. I've got so many projects, you guys. Okay, I know it's so hot, but just brace yourselves. I was part of this really cool experience at Berkeley where, and Madikin here was part of it too, kind of, where there were all these people who were doing science and what could kind of vaguely be called data science within their sciences, and we all sat together in a room like this with exactly these same chairs. It was a really hip space, and it actually sort of brought up a bunch of questions around what the proper way to actually do reproducible research is. And we basically got together a whole bunch of scientists who were trying really hard to be reproducible. And we said, okay, what are you doing? And we had a workshop, and we had everyone write a flow chart of where their data comes from and where it goes and what script runs it. Oh, sorry, that's my don't talk too much alarm. What script runs it and who deals with it and who does the analysis and where does the plot come from? And we put all these case studies together into a book, and I had the pleasure of reading through all of them and pulling out lessons learned, right? So that was my job as part of this book. And it was one of these experiences where I felt a lot of pain, like of those authors. I really felt connected to the people who had written these things. Everyone wrote a few pages on like how their workflow worked that like came together with this this diagram. Some of the other so the editors of this diagram are of this book are Justin Kitzes, Fatma Imamoglu, and Daniel Turek. Ben Warwick helped a whole heck of a lot, and there are a lot of chapter authors and case study authors. But I'll just say this is what these workflows looked like. Some of them were really complicated. Everyone was given like a lot of freedom. Some of them had data input and data output and theory and not theory and exploration. Some of them had like real sections. Some of them didn't. And this is sort of what that workshop looked like. It was invitation only, so we only invited the people we thought were trying really hard. Some of them made insane flowcharts. This is after editing. This is the things that they hold in their head to keep their workflow working in science. And we asked, like, why do you try? What hurts? What kind of recommendations would you give someone trying what you're doing? And then I did a little data analysis on the text itself to see like what exactly they really were doing. And we identified some needs. So I'll just say most people did it so that they could collaborate better and focus on science. If their code is definitely going to work, they can focus a little better on science. And a lot of people said that they wanted verifiability and extensibility so that graduate students working with them could leave and it's not the end of the world. And so they tried to make their code reproducible, but the things that hurt, by and large, the vast majority of people, their biggest problem was with people and varying skill sets. Almost everyone had a large group of collaborators, and no one, or even small groups of collaborators had this problem, but it was never the case that everyone had exactly the same software stack like available to them. And so-and-so wants to write the paper in LaTeX, but, this guy would rather write it like in his like nice overleaf experience. So it's kind of LaTeX, but it's not. But they want to version it in Git, and so they have to do this whole thing. And someone wants to write in Python, but this guy only knows R. Is a huge problem for most people. Dependencies build systems and packaging. Building things on computers is hard. Having access to various hardware made things reproducible. Some people work on fMRI machines or Stellarator, right? Do you have a Stellarator? Like University of Illinois has one. But it's really hard to reproduce the science done on something like that because there's only a couple, right? Do you have another Large Hadron Collider, right? Will you be reproducing the work that's done there? So that's a hardware access problem. Testing was hard, like getting incentives to do that. Publishing was hard. Data versioning was hard. All these things are the things that were hard. Data restrictions were mentioned by a couple people, mostly in the medical sciences and in nuclear engineering. My own field, where you can get arrested for sharing too much. Right. Everyone said version control, open your data, test everything, use open tools. We've gone over these things, but all of those people agreed with all the things that you and I have just been discussing. The recommendations also included some kind of clever things, like if you can avoid depending on some package, avoid it. Because it's like really hard to build new dependencies into your software. Or at least package their installation, put it in a Docker or something. Host your code on GitHub. Get digital object identifiers for your data and code. We can talk about that more later, but I'll just say like there's some like clever stuff here. I'll let you just read them. I'm supposedly allowed to talk for 40 minutes, so I have 4 more minutes. Okay, so I'm going to skip these outliers, but I'll give you some data. So I looked over everyone's workflows and said like what tools are they actually using. GitHub was the most common. Python was the most common language. Everyone tried to use LaTeX. R was the second most common language, and lots of people were using Jupyter, but not as many as I expected. So we had about, 30 case studies or something. So I expected a lot more of that. So language use, like we had some multiple language projects, but it was mostly Python and R. People have kind of abandoned C++ and Java for like really reproducible software development in science. Interestingly, this is my most favorite graph of this whole talk. Python users are in pink. People who use both R and Python in a single package are purple. R users are blue. On this side here, the people who are trying to do their best, half of them or so wrote tests. slightly less than half. Here on the other side, everyone who didn't write any tests, so there's like 30-ish people total. They either wrote tests or didn't write tests. And there's about the same number of Python users in both groups, but so many more are R users in the no test group. And we know why that is. It's hard to write tests in R. There's only one like widely used R testing framework, and no one uses it. So this is a huge problem, and I'm worried about everyone that uses R, and we should all be worried. That's the conclusion of this graph. Python users have like a fleet of Python unit testing libraries to choose from. Our users have just one, and no one uses it, to my understanding. All right, we'll skip forward, and I'll just say, as a last sort of like cool thing, I work on this journal for open source software. This is the brilliant idea of a wonderful person called Arvin Smith. He used to work at GitHub. Now he's back doing science. But generally speaking, there's a whole bunch of cool people. Sorry, I just skipped over them. All right, here they are. All the coolest people in the world are on this. Okay, not really all of them, but like a very remarkable set of people are on this, including Jake Vanderplas and Karthik Ram, Tracy Teal, who's now running the Carpentries. So some amazing people are editors of this journal, and it's on GitHub. And we now have 232 accepted papers. We've been around for about a year and a half. And the way that it works is that you have some open source project. Let's call it Baskets. And you have a repository where you host Baskets, and you and all your academic collaborators are working on Baskets. And yeah, okay, sometimes you produce a paper that's related to Baskets, but like no one can ever really cite Baskets, right? You could create a Zenodo ID for it, but it doesn't go on your CV. You could create a DOI that like is a digital object identifier for Baskets, but it doesn't have any kind of academic merit. No one's ever said like, we approve of Baskets, right? JOS does code review on Baskets. So you submit Baskets and a short summary of what Baskets is capable of to JOS. So you tell us where the GitHub repository is, or Bitbucket or whatever, and you send us a markdown file, which is usually in the repository, ideally, and we check for a whole list of useful things. Mostly the things that I've just listed in this presentation. Does it have tests? Is it documented? Can I build it on my machine? So the reviewers are asked to take a moment, go build this software, go look at it, review it, run the tests. Does it work? Do we like it? Does it do the 6 things that the markdown file says it does? It's a very fast review process, but we typically help most of these software projects get some of those better practices in. And then there's like a citable thing that has been reviewed by other academics who do scientific software in your domain. And it's like a real paper because we're indexed on Google Scholar now. So take that. And we have a paper about our journal. So you can read all about JOS as of like a few days ago. So we reviewed the first year. So if you're interested in JOS or submitting to JOS or reading about how JOS works or taking down the whole model and telling us what we're doing wrong, let us know. Super cool. So that's all I really have here. Okay, I should say a lot of these thoughts came from my personal experience, but a lot of it is, from conversations with colleagues across my whole universe and life. So thank you to them. So yeah, I'll just end it here. And you can find the slides right there at this link, which it's just a URL. Thank you. Yes.
Quick questions. What event happened in 6th century BCE that you referred to at the beginning?
Yeah, so this was like the beginning of Plato's sort of, Plato, stuff like that.
What's this satellite?
It was post-Plato, so I should say like this, sorry, a stellarator is a,
What is it?
it's a stellarator, it's a type of toroidal. Okay, the current question is what is a stellarator? And the answer is it's a toroidal fusion device, but it's not like a boring toroidal fusion device. It's not just a tokamak. It has a weird twist in it for some reason. Great question. Other questions? Yes?
Now, are a lot of people doing work in either fission or fusion? And tokamak was, I think, the first fusion device. Are a lot of people in the fission or fusion world using open source software?
Some of them are. Sorry, we have a couple of nuclear engineers in the audience, and they are, in fact, doing so. I do, with all of my software, with my research group. My PhD advisor, who I actually owe most of my intellectual ability these days, is Paul P.H. Wilson at the University of Wisconsin. We're not alone. I would say that there's a small but growing population of people who are trying to do nuclear. There are a couple things we're not allowed to share, like certain cross-section, like probability information about certain nuclear reactions we're not allowed to share, for example. What's up?
When you try to design such a code for something that you want to do, and for example, I'm a nuclear engineer too.
Excellent!
And one of the problems I run into is while I code, everything is fine until it works. The moment it works, somebody wants to have it under security control because it works.
Oh.
How do you make something that was open source and you wanted it to be open source available to the community, but through a censorship?
Through a censorship.
Like RSIC.
I don't. I would make it, if you could, make it be born open source, and slap an open source license on it, and wait for someone to complain. That's my current strategy. Shouldn't say that on YouTube. I would say, though, that you do have to be careful, and if you have a piece of code that you must go through RSIC for distribution, a number of pieces of code, like Serpent, for example, they typically try to send the source to most of the people that they approve. Is it an open source model? No, because no one has access to the repository. Can you run the test? Yes, locally. Not really it's bad. It's a tricky situation.
But what can we do about it as a society?
As a community?
We all agree that some of these things shouldn't just be shared globally. But we still want to share them with the people who do want to share them.
Yeah, okay, so for really, all right. For some of it, I think we do have to rely on the government's RSIC program to vet people. And internally, RSIC should probably have a GitLab instance. Maybe someone should go work for RSIC and give them a GitLab instance. It takes an undergrad for a summer. It's not that hard. Just setting up all those codes on GitLab. Oak Ridge has, so a few different labs. Labs have various GitLab instances just for their labs. So Idaho has one, Oak Ridge has one. And you can log in with your Oak Ridge credentials or your Idaho credentials. That's probably the answer.
Suggestion, just have a private repo and share access or add access to the trust.
This is true. So who you trust, though, in nuclear, I think what he's getting at, you're totally right. For most people's application. For nuclear, who you trust is determined by the government. So we have to actually let this group called RSIC deal with it. Thank you. There's so many more. Okay. Yeah.
Lot of fantastic best principles. Not all the scientists I work with are using all those principles yet.
Yeah.
Is there an advantage to introducing those principles to them incrementally? And if so, what would you start with?
Definitely incrementally. I would start with version control. Sounds brutal. So his question was, lots of scientists don't do this stuff. You guys came here knowing most of this stuff. Hopefully you learned at least a couple of cool, fun buzzwords that you're going to go Google. But yeah, the real takeaway is that you're the foot soldiers on the ground to encourage your colleagues to do these things better. And now you have a few reasons. You got a paper you can show them. But what do you teach them first? I think that most scientists are blown away by the capabilities of version control. As soon as they really get what the power is, that they don't have to have 70 folders called, run 1, run 7, run 92. That's a real game changer for a lot of scientists. And I think as soon as they really get it, I've seen people, particularly at software carpentry workshops, I've seen people become just devotees. That's why there's so many software carpentry instructors, in my opinion. Is anyone here in software carpentry instructor? Yeah, okay. Yeah. In my opinion, a lot of people become software carpentry instructors because they're sitting in a boot camp. They realize, oh God, this is going to change everything. And it's usually in the version control part, in my opinion. What's up?
We know that scientists generally are reticent to adopt some of these best practices, just like was just said. But how do you feel services like Pachyderm are going to break into that environment where you can actually version control their entire workflow and their
So there's something called, I don't want to kill everyone, but I could talk about this for a while. There's a significant difference from the scientific perspective between replicability and reproducibility. So packaging your whole system and just like preserving it in its state as a complete virtual machine, that is replicability, because you will run exactly that code in exactly that way. And reproducibility is a little different. I think computational reproducibility is kind of in between real like traditional scientific reproducibility, where you run another experiment exactly like that first experiment at a different lab somewhere else, and you have your own beakers, I don't know, whatever wet lab scientists do. That's not my jam. And then replicability, which is this like virtual machine sort of scenario. So that's like way over here in replicability, and it's like you're doing it exactly with exactly that machine. Computational reproducibility that I'm trying to get at personally is this thing kind of in between, where you're running same code, maybe with new parameters, and you're testing the conclusions based on the software that they've written, because you understand the tools and software. But this virtual machine, that's the virtual machine, that's the kind of thing that it's just rote repetition. Does that make sense? So it does change things for some people, because then they can at least send their software somewhere without worrying about Docker. Okay, all right. Maybe, I don't know. Who's in control? I don't know when this has to end. Okay.
So basically, those are the rules that software engineers live by.
I think so, yeah.
But are there any of those rules or like changes in those rules that are specifically, you think, more suited for scientific workflows and for scientific work, or like more important for that?
Yeah, so I think software development in general, it's okay for something to be a little wrong. Your GUI's like a little off, it's the wrong color or something like that, or like, your data analysis is like a little fuzzy in some angle, but like you're going to get the same conclusion. Because in science, you really need to get it all quite right. And so the testing part, and really like deep unit testing of all of your assumptions, I think is so much more important in science. I think you guys can get away with a little less unit testing, frankly, than scientists really should be getting away with. And the opposite is true. I think you guys do a ton of testing. I say you guys, I know not all of you are in like the tech industry, but like I would say that like software development in an industry does a lot more unit testing than maybe they absolutely need to. Whereas in science, like we should be doing vastly, vastly more than we are now. Because it's really that like testing of your own assumptions and being able to like extend a current piece of software. Like I don't know how long a single piece of software lives on at Facebook, but I don't think it's as long as, for example, the Monte Carlo neutron transport code that nuclear engineers have been relying on since the 70s. Yeah. Okay.
Right. Do errors with like floating point error detecting, does that ever or does that ever really affect?
Do floating point errors ever impact reproducibility, or like, for example, just science in general? Yeah, I actually use the decimals package pretty often in Python. So there's a SciPy, I think there's a decimals package which allows you like explicit representation of decimals type numbers rather than using the floating. It's like not very memory efficient, but do I want it to be memory efficient or do I want it to be right? Typically, I want it to be right. I got memory to spare.
Last question. So I think some of the things you described probably be surprising to many scientists. And I'm wondering, based on talks even all the scientists before, but how much of this gap, which we should do and we are doing, is due to people not being aware of these practices, and how much of it is due to tools not being very usable that easy to integrate into a normal scientific
I love that question. How much is it due to scientists not being aware versus the tools not being tooled up well enough for them? I think it's mostly awareness. But I'll also say Git could have an easier user interface. Like why are there two meanings of the word checkout? And why is it different than the one that SVN used? I think that those things are a little confusing for people. But I would say it's mostly awareness. And I'd also kind of go, I don't want to abuse any scientists, but I'd go slightly further and say scientists can be aware of a thing without truly believing that it's right. Like all humans, we need a lot of proof to believe that this is the thing that we must do, and I think there's not as much incentive as there could be, even for the things that we're aware other people are doing and probably are right, or maybe hard. This is like a little slow to admit which things are worth our time. So there's that problem. There's sort of a inertia. Thank you.
So with that, I want to welcome everybody to stick around a little bit longer, but also want to acknowledge again Dr. Patricia Schuster for having Katy join us today. And can we give Katy a round of applause for this?
Thank you.